I wouldn't forget this one in here in the corner. Let's remember how to construct a Taylor series. What's it mean if I say Taylor series versus Maclaurin? Is the process very different between those two? What's the only difference between Taylor series and Maclaurin series? Yeah, the value of A. And really it's what, you might hear me sometimes say, I'm going to build a series around 7 or 0 or 2. If I build it around 0, that means A is 0, that means that's Maclaurin. Anything that's not 0, that means it's Taylor. Right? Okay, I like it. So Maclaurin is just a special case of the Taylor series, where A is 0. Okay. We did this crazy derivation where we started with our function and the way we wanted it to work, and we sort of did derivatives, and we constructed the CNs. I don't know if you remember that day we did that. So if you weren't here, you want to watch that video, or not. But we eventually got, does anyone remember the form of the Taylor series given some function? Yeah, the nth derivative of x, of f of x,
over n factorial.
n factorial.
Times x minus a of n.
Yeah. So this is just our Cn. Okay, so again, we're used to CNs just being given to us. Like on the quiz, I just gave you a C, I just made it up, right? That was just me going, let me put an n here and a 2 in here, just making shit up. Just like I could make up, I could here. Does this look like a graph of a function? Sure, right? But I can be given a function and then make its graph. I can be given a function and I can make its series. In order to do that, I have to have a way to figure out what all the CNs are. So the way it turns out, it's this. And let me show you, somebody tell me what the first, in fact, I got one little mistake here. There we go. Put a little A there instead, right? Let me ask you this. Let me take us back a little bit. Do you remember in Calculus 1, when you had to construct a tangent line? You had to find the equation of the tangent line. Do you remember those problems? If you don't, it's a little weird, right? Because you did that all the freaking time, yes? It's one of the most common problems throughout all of calculus. So real quick, just hear me out. If I have a function, square root of x, and I want to find the tangent line at 4, 2. Is that cool? I could have made it 9, 3, whatever. It just has to actually be a point that exists in that function. I love it, I love it. How would you do this? This should be a gimme problem, right? Fine. In fact, you guys do it right now. I want the equation of the tangent line to this function at that point. Go. That's a gimme problem. I'm sorry, I keep saying it. If you forgot, okay, we'll talk about it. You can either use this guy, right, eventually, or you can use mx plus b, right, whichever one you like better. What's the very first thing you have to determine?
Derivative.
Yes, because I already have what x1 and y1 are, right? Mm-hmm. I know what that is. 4, 2. Yay. x1 is 4, y1 is 2. The only thing I'm missing is the slope. And of course, we're better than algebra now. Algebra, you actually needed 2 points. And then calculus came along, and you only need the 1 point. Because I can directly get the derivative. What's the derivative?
Over 2 root x.
Yeah. Be 1/2 x to the negative 1/2, so it'll be this. So what is the slope of my line then? What does this function actually tell you? You guys remember from calculus? What does it really tell you? Be more explicit. I can tell you the slope of a line. If I have the line 3x plus 7, the slope is 3. That is the slope. But you can't say for something that's not linear, you can't identify the slope, because what's happening as you move it along it? What's happening as you move along it? The slope is constantly changing, yes? So when you take a derivative, you are finding a function that gives you the slope at any point you plug in, right?
Oh, yeah, you plug it
Right?
more, yeah.
And again, in calculus, teachers are guilty of this. We'll kind of go, derivative of slope, and just slam in your head, derivative of slope. You're like, okay, derivative of slope. That's not good enough. Derivative is the function that will give you the slope if you input what point you're at. Okay. So, what's the derivative that I need to use then? I want to plug in what to my derivative formula? 4, because that's the point I'm at. So I mean 1 over 2 squared root of 4, 1 over 2 times 2, 1 over 4. Is that cool? So then to finish this up, y minus the y piece equals the slope times x minus the x piece. So I get y equals 1/4 x minus 1 plus 2. Is that cool? And let me go one step further. Believe it or not, this is going to relate to what we're doing. Right? Let me go one step further. How could I use this to estimate what the square root of 4.24. Yeah, I love it. I want to estimate what the square root of 4.24 is. So don't I have a linear function that approximates the value of this close to what? I have a linear function that approximates the values for this function close to what input? 4. Because I built it around 4. At 4, this is perfect. What do you get when you put a 4 in? 1/4 of 4 is?
2.
Okay, gotcha. Yeah, 1 plus 1, 2. And when you plug a 4 in, you get 2. So if you put the point you built the thing around in, it's perfect. The minute you get a little bit away from it, this thing curves and this thing don't, right? So when you zoom into a function, I'm sure your teachers in Calc 1 did this, you put it on decimals, you zoom in, and then it's flat, sort of like we're on the earth. And there are some people that think the earth is flat because they're like, look. I'm like, oh shit, right? So we're so close to the surface, we're like, oh, it looks flat. You zoom out, you go out into space, and we have pictures from space, and you can see his curve. Okay. So, it's just one of those things. Okay, is everybody with me? So we did linear approximations. You can throw something in. So if I put a 4.24 in, you can actually do this without a calculator. 1/4 of 4.24 plus 1. 4 goes into 4 once. 4 goes into 0.24, 0.06 times. So I get 2.06. Can somebody tell me what's the square root of 4.24? This is me wishing I had an embedded calculator.
The square root of what?
4.24. I'm saying it's about 2.06.
2.059.
Is that pretty good?
Yeah. For us humans.
For us humans, and it's good for government work, right? If I put square root of 11 in, would that work as well? Would my approximation work for 11?
No.
Why not?
That's
Because I got really, really far away from 4. So again, what's a square root function look like? That's right, kids. And what's my linear function look like? So at 4, it perfectly lines up here. If I get up to 11, then how different is my approximation to my actual value? Very. Okay. Okay, everybody with me? That's old news. That's all old news. You wish to God I would give you this problem, and I'm not going to. It's too damn bad. So, but I'm going to keep this up here. We're going to construct the Taylor polynomial for this. And then I want to show you something interesting. Okay. So let's do it. So what's the process for constructing a Taylor polynomial? Good Lord. Well, let's construct. So I'm given polymole polynomial, that's good, Jeff. So I'm given this function, and I want to build a Taylor polynomial around x equal to, let's just say a equal to 4, same thing. So does anyone remember the first few steps of how to do this? What do I need to make a list of? Derivatives, because again, this guy requires a list of derivatives evaluated at the input. So let me make a list. So let's see, our function is x to the 1/2. And what is f of a? 2. Amazing. Okay. F prime of x is 1/2 x to the negative 1/2, right? So what is f prime of 4? Yeah, 1/4. I love it. Now notice something. I want you to notice. Let me write this a little bit. Let me write this closer to what we had first. This will happen sometimes, often enough. I already know what this is evaluated at 4. So anytime I see it later, I just put a 2 there. I already know that's 2. You guys understand what I'm saying? When I plug a 4, I'm going to get a 2. Wherever I see next to the 1/2, it's going to be 2. What's f double prime of x? Did I put a +1 there? Did I mean to put a +1 there? Yes. What's the second derivative? So this is where we really want to have it written as 1/2 x to the negative 1/2. So what's the second derivative? Negative 1/2 comes down?
Yeah,
negative 1/4.
And times x to negative 3/2 prime.
So it'll be positive 3/2 on the bottom. Is that cool? You guys all with me? I'm just doing derivatives, so if I ask you to do several derivatives, you're like, yes, please. Should be anyway. So what's f double prime of 4? We negative 1/4 times. Yeah, 2 to x to the 1/2 is 2.
Yeah.
2 cubed. 8. I love it. So 4 times 8. 32. Stop for a minute. Is that cool? X to the 3/2 is just x to the 1/2 cubed, and I know x to the 1/2 is 2. Let's do a couple more. Third derivative, negative 3/2 comes down, so that makes it 3/8. The negatives cancel, and the power goes down by 1, 5x. It's pretty cool the fact that I just took the power down by 1, but it went up to 5. Because it's a negative power. Okay. And then f triple prime of 4, oh shit. Square root of 4 is 2, 2 to the 5th power is 32 times 8. 256, right? Okay. All right, I think that's enough. I think that's enough. Before I go any further, do you notice a pattern in the derivatives themselves? Not these. These. You notice a pattern here.
Yeah. It's alternating.
So it's a little weird on the top. I'd have to do another one to see what's really going on the top. But the bottom certainly seems to be 2 to the first, 2 squared, 2 cubed. Right? So it seems to be. So the third thing is 2 cubed. So it seems to be 2 to the n. Right? You guys see that? X to the, this gets a little funky. First one is a 1, the second one is a 3. Third one is a 5. So it looks like odd powers, right? X to the, let's let's see, what would it be? So the third one's a 5, so it'll be 2n minus 1. Yes. You can do it, John. 2n minus 1 over 2. You guys, is it brutal? Really?
Kinda.
Not really.
I've
So
never
I'm
seen
taking it one step at a time, right? That guy is powers of 2.
Oh, yeah,
The top of this, the bottom's 2. Bottom's 2.
yeah.
The top of it is odd numbers, right? At least for these guys, right? Now the top is the weird one. The top is the one I'd have to probably do another one to see what the top does. You guys kind of follow? I knew I should have done one more. Let me see. Can I flip that in? Let me put this up here. It looks like the nth derivative looks to be, what do we have so far? 2 to the n, x to the 2n minus 1 over 2. And now we just got to figure out what the top is. So let's see. Let's do one more derivative. This should be really exciting. Let's see. At the fourth derivative, negative 5/2 comes down.
15 over 16. X7.
So everything kind of follows the pattern. Now, of course, we should have a negative 1 to the n kind of thing going on here, right? Negative 1 to the n plus 1. So the top is looking a little interesting. Multiply by 3, multiply by 5, probably multiply by 7 next, I'll bet, right? So I have to keep going. So if you wanted to find, now, if you looked at these, it's very often harder to see the pattern than it is to find the pattern here. So what's this fourth thing at 4? It would be negative 15 over 16 times 2 to the 7th. 2 to the 6th is 64. 2 to the 7th would be 128. Is that right? Yes. 2 to the 7th is 128.
Oh, yeah.
Okay. And then 128 times 16.
181.
What is it?
181.
No, it can't be.
No.
128 times 16. Yeah. 256. 512.
2048.
2048. Mark. Neato. So anyway, if you wanted to find the pattern in those, you'd have to go far enough out. Looks, you guys, I think at least a few of you came with me on the bottoms of these. Yes? This is obviously powers of 2. No question. The bottom of the fractional power is always 2. That's easy. And the top is just an odd number. Okay. I'd have to do a few more to really figure out, but it looks like this is 1 times 1, 1 times 3, 3 times 5. So I bet you the next one's going to be times 7, right? It looks like I just keep multiplying by the next odd number, correct?
Yeah.
Okay. That's all, believe it or not, that's all a side note. I'm just showing you how you could find the pattern if you needed to. So let's try to write out a few elements of this polynomial. Let's see. So I've got, let me see, what's the first thing look like? So if I write out this, let's put a 4 here. So when n equals 1, I'll get f of 4, which is 2, over, when n equals 0, I'll get f, the 0th derivative evaluated of 4 is 2. 0 factorial is 1. X minus 4 to the 0 is 1. Plus. When n is 1, I'll get the first derivative of 4. First derivative value of 4 is 1/4 over 1 factorial times x minus 4 to the first. With me so far? I'm just kind of throwing stuff in. Plus, now it's going to be minus 1 over 32 is the f second derivative at 4 divided by 2 factorial times x minus 4 squared. Let's just do one more. So that is going to be plus the third derivative evaluated at 4 is 3 over 256 over 3 factorial times x minus 4 to the third. And there's more stuff out there. So look what I get right here. I get 2 plus 1/4 times x minus 4 minus 1 over 64 times x minus 4 squared plus x. Look at the first piece though. If I simplify this a little bit, isn't this 2 plus 1/4 x minus 1? Isn't that 1/4 x plus 1? This is the first Taylor polynomial. All Taylor series do is they add on extra terms for the higher derivatives. So this, if I stop here, this is a straight line, this is the tangent line at this function at 4, and it doesn't hug it, it's only good right close to 4. If I add this next term in, and I can kind of FOIL that out, I can blah, blah, blah. If I put that next term in, this next term makes the curvature match at that point. So if I had, instead of a straight line, if I had something that could curve itself, couldn't that fit a curve better? Yes? So instead of having this situation, I want to have a situation where the little dude can match the curvature there. And then I keep going. The concavity, and then I can make the third one match up, but that whole business there. So when you did linear approximate, when you did tangent lines, which were really the same thing as linear approximations, you were doing the first order Taylor polynomial, and you're doing T1. You're stopping at n equals 1. You just didn't say that shit because you didn't know what the hell Taylor series were. Yes?
So that whole thing is a formula? Like if you put it in the
Yeah,
calculator,
dude.
it'll be curved?
So let's do this. Yeah, let's just go out to the, I think this is fine. So this would be T2. I went out to the second degree, right? Help me out. This first thing, when we did this, instead of 4.24, let's go further away. Can we approximate what the square root of, what do you got, Chad? Square root of 7, right? This should not work very well, because 7's pretty far away from 4. So let's see what we get. If I put a 7 in here, 1/4 of 7, 1/4 of 7 is, what is that, 1.75, so you get 2.75? Is that right?
Yeah.
Yeah. What is the square root of 7?
That's one, I think. Oh yeah.
What is the square root of 7?
2.65, 2.645.
Okay, so that's not horrible, but it's off by 0.1. That's getting a little worse. All right, let's try it in here. What if I put 7 into this guy? 7 minus 4 is 3. So I get 2.75 minus 9 over 64. Whatever the hell that is. 2.609? And what was the actual answer again?
2.645.
That's a lot closer now, right?
Yeah.
So what's going to happen if I keep going further into the polynomial?
It's going to get more accurate.
So real quick, is that below or above the actual answer?
Below.
Below. See how the next term is positive? So you're kind of like zeroing in on the actual answer. When is the only time you get the exact right answer?
Infinity.
If you go out to the infinite degree term, right? I love it. Maybe. That's why the most use we get out of this in like everyday sort of real immediate life is to stop it somewhere. And where do I stop it? Wherever I'm okay with being wrong, right? I stop it to a certain decimal place. Yes? Okay, maybe. Okay. So let's do another one. Let's see. Let's do one that's kind of already done, just to verify it. And then I want to show you a couple things you can do with this stuff. Okay. So the important steps here were get a list of all the derivatives, or as far as you want to go. Evaluate all of those at A, and then put those into the form. Construct your polynomial, right? Okay. So let's try another one. We'll get to. In fact, last time did we do sine, or I think we did sine, and then we got cosine by taking the derivative.
Yeah.
Okay, let's do cosine. Let's actually prove cosine. Even though cosine's a little bit boring.
So on the test, when you ask us this, you're gonna tell us how many
Yeah.
derivatives you want?
Yeah, I'll either tell you, so if I ask you to find like T3,
Okay, yeah.
I mean stop at the third term. Let me make sure they use the same terminology I do. Here we go. T2. Okay, good. So like good, perfect. I think this is 2. Yes. So T3 would go out to the third power, right? The third derivative. Okay. That's the kind of question I like to answer the most because very often it's difficult to find the pattern in the Cn terms. It's not the easiest thing to see. But let's try this. Let's do cosine, and then I want to try to do this problem. So given cosine, let me give myself some more room. Given cosine, we make a list of the derivatives. Let's do something. Let's do this. Let's make this a little more interesting. And you're like, why, Jeff? Let's make a cosine of 2x. I like it. Okay, what's the derivative of cosine 2x?
Negative 2 sine.
Negative 2 sine 2x. Second derivative.
Negative 4 cosine 2x.
All right. Third derivative.
Negative 8.
Yeah.
Or no, sine. 8 sine.
Positive 8.
Yeah, positive
Good.
8. Sine 2x.
Sine 2x. So it's going to be pairs of same sign things. Fourth derivative.
16 cosine.
16 cosine 2x. So what is the derivative? That's a little weird. If I ask you for the odd derivatives, they're going to be a power of 2 times sine 2x, right? And the even derivatives are going to be a power of 2 times cosine 2x. Okay. So let's do a Maclaurin. Actually, got our T. Let's do a Maclaurin. What does that mean? Maclaurin series. A0. I love it. So then I want to evaluate each of these at 0. And that becomes very, very simple. We might have to do one more. Let's see. We have to do 2 more, actually. So what's f of 0? 1. Cosine of 0 is 1. F. What is going to be true about every odd derivative?
0.
It's going to be 0, right? So all the odd derivatives are 0, because sine of 0 is 0. What's the second derivative evaluated at 0?
Negative 4.
Negative 4. Fourth derivative evaluated as 0, 16. Let's do two more real quick. Make sure you can see that negative. So then we get the fifth derivative evaluated as 0 is 0, and the sixth derivative evaluated as 0 is negative 64. Oh boy. Okay. So what do you think how do I say this? If I want to know what well, let's write a few terms down. Let's see. We can do this. So I got my general form. Okay. And I might as well just go ahead and write 0 in here. So this is just x to the end. It's the Maclaurin series. So the 0th derivative is 1. And then you get a 0. So 0, 1, 2. So when n is 2, what do I get? I get minus 4 over 2 factorial times x squared. Right? I really want you to understand that as weird as it was to go through the derivation of Taylor series, the construction of them are very, very straightforward. You just do a series of derivatives, you plug the value you're interested in, and then those numbers get fed into the thing. That's it. So then we get plus, so now this is second, third, fourth. So the plus 16 over 4 factorial times x to the 4, right? Yes.
Just wondering, so we start at n0,
Yes.
so then wouldn't that make like the second one, what do you call it, 1 factorial?
Yeah, this is n equals 1. And it has a 0, right? That's
Yeah.
why it doesn't show up. Yeah?
No, the second one.
So that would be 2. N equals 2, so that'll be 2 factorial. Yeah. The n equals 1 doesn't show up because it's got a 0 coefficient.
Okay.
Okay. Good, yeah. Okay, you guys with me? So this is a very much a construction process. You construct, you get the parts and you construct it. And then the last one here would be minus 64 over 6 factorial x to the 6. And now you see the pattern sort of. So if I want to capture the pattern, it looks like, what would it be? Did you guys see the pattern? 4 to the, is it 4 to the n? So let's do 2. Maybe 2 will be better. Because at the fourth term it's 16, right? So it's 2 to the 2n. Let's see if that jives with you. Try that out. When n is 0, I get 1. When n is 1, I get 2 squared. When n is 2, I get 16. Anyway, so that's capture that. Over 2n factorial times x to the 2n. Oh my gosh. Let me stop for a minute. A bunch of 2n's in there because I have a bunch of, what do you call it? Even numbers. Yes.
Explain how do you get 1 for the first one?
Yeah, so f of 0 is 1, right? The 0th derivative of f evaluated as 0 is 1, divided by 0 factorial is 1, times x to the 0 is 1. So, yeah. Okay. And of course this keeps going forever, plus blah, blah, blah. And then we can clean this up a little bit. So this is like what it looks like the nth term would be here, but if I clean this up a little bit, I'll get 2x squared plus, what's 4 factorial? 12, 24, 16 over 24 is something, 2/3 minus 6 factorial. Let's see, 6 times 5, 30, 16 over 30, 6 times 5 times 3 times 2. That'll be, this is exciting. 8 over 15 times 6, which is 4 over 15 times 3, and I think it's 4 45ths, maybe? Is that what that is? I don't know.
4 45th.
No way, okay. No, that was lucky drunk math, okay. And then blah, 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 blah. So I want you to see, before you simplify, you can capture the pattern. Once I simplify, that is not an easy pattern to see what's going on. Okay, so that is cosine of 2x built around 0. So I could use that to estimate cosine of, let's say, point, what do you want, Jeff? 0.2, sure. If I want to estimate what cosine of 0.2 is, using what we just did, can somebody tell me what x is? What function did we just create a series for? What function did we just create a series, cosine of 2x? So if I want to estimate cosine of 0.2, what is x? 0.1, right? You got to make x 0.1 in order to get the question I want answered, yes? So that means I'm going to plug a 0.1 in here. So it'll be 1 minus twice 0.1 squared plus 2/3 times 0.1 to the 4th. That'll probably be plenty. Let's see what this is. 1 minus 2 over 100, so 0.02 plus, oh jeebus, 2 over 3, what is that? 1, 2, 3, 4, 2 over 30,000. Isn't that neat? Because that's 1 over 10 to the 4th power, so it's 1 over 10,000 times 2 over 3. I love it. So I get something. I don't know what that is. Help me out, guys. I know this is 0.98. How much I know? What's 2 divided by... Does everybody see where I got this last dude? Right, x is 0.1. Plug a 0.1 in. There you go. Does anyone have what this is?
0.98006666.
Oh, neato. I mean, a beautifully evil number. I love it. Now, can somebody please do the cosine of 0.2? What is? Make sure you're in radians. Yeah. And then I want to ask you guys why you have to be in radians, but.
Cosine of 0.2 is 0.9800665.
Shit. I mean, did we go very far out in the? How many more terms on it? Infinite number. All right. Well, we stopped at like this term. That's crazy, and it's already that close. Now you could ask. A good question would be, okay. In fact, let me ask you this. Not just do I want to stay close to 0 with this number. What else is there about power series that tells me I have to be careful about what values of x I can use? Any power series you get, can you use any value of x you want to? What's one of the main things on the quiz?
0.
We give you a power series. What do you figure out first? Interval convergence. If you have a function that you want to know its domain, so you know what you're allowed to plug in, right? Now I felt pretty good about 0.2. It's really close to 0. But we'd officially have to figure out, we'd have to do a ratio test on this to see what its interval convergence is. Do you guys understand?
Yeah.
Okay. Now, real quick, I was thinking about making a worksheet that showed the steps, but these are the frickin' steps. There's really, you do a series, you write the function, and you do a few derivatives, right? You normally can get by going out to the 4th or the 5th, but you might have to go further, especially with something like this, where every other one is 0, you're like, ah, shit. So you gotta go a little further, right? In case you need to see a pattern. All right. And then once you got these numbers, you plug the freaking thing into your derivatives, you get these numbers, you just plug them in. You just put them in. So when n is 0, this goes in. When n is 1, ooh, shit, that's dead. When n is 2, this goes in. So that's 2, right? It kind of constructs itself. Not as bad. And again, I know somebody out there is like, I still don't know what the shit you mean, Jeff. I don't know what you mean, but I need you to understand it's not as weird as it seemed when we're deriving how to do it. Actually doing it is pretty straightforward. So, all right, I want to do one thing. I'm going to keep that up there. Can somebody tell me, well, let's see, what did we do last time? Last time, I need this for this anyway. What was sine of x? We figured out what sine of x was. I don't know if you guys remember. Sine of x and cosine x sort of like went together really well. I'll get us started with this. So it's really kind of cool. Like that, right? And again, it's on page 804. 804 is your friend. Page 804 is your friend. It has got a list of all the known, or not all the known, but enough of the known Maclaurin series to kind of reference, right? Cosine x is just the derivative of this. So without going through all that again, we basically get all, notice how this is all the odd stuff? Cosine is all the even stuff. It's kind of a beautiful little blah, blah, blah. The next one will be minus, but that's blah, blah. So watch this. What should cosine of 2x be then? If this is cosine x, how do I figure out what cosine 2x is?
Just substitute x for 2x.
Instead of just putting an x in, I put a 2x in. So it'll be 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial, which is 1 minus 4x over 2 factorial squared, sorry, plus 16x to the 4th. Does that look familiar at all? Right? So again, if I have a series for a function, if I've already created a Taylor series for a function, anything that is just the same function with a different function of x on the inside, I can construct it without doing all that shit. I already know cosine x, so that means I automatically know cosine 2x. We went through the steps and we got this, but if I just do it directly from what cosine x is, I also get that. I don't have to go through all the work. So if you construct a few building block functions, you can pretty much construct a ton of other functions by messing with those. Okay, maybe. Like, how do you, and here's the funky one. You ready for a funky one? How would you figure out tangent x? What would you have to do? Yeah, it's equal to sine x over cosine x. Which is sort of like a nightmare. Can you imagine? What's sine x? All this business. X minus x cubed. Well, I'm going to put the numbers in there. Over 6 plus x to the 5th over, what is that, 120? Divided by 1 minus x squared over 2 plus x to the 4th over 24. No, minus blah, blah, blah. Okay. Now they actually do this in the book with, I can't remember if it's exactly this problem. You can do this. Do you know how to do that? Do you know how to start to do this division? You do, I know you do. You do, you just don't want to. And I'm not saying you're lying to me, I'm just saying your brain is like, no, say no, we don't. Okay, I just want to, we're not going to do it, right? But do you see what I'm saying? 1 times what is x? X times 1 is x. x times negative x squared over 2 is negative x cubed over 2. X times x to the 4th over 24 is x to the 5th over 24. Subtract. Let's keep going, right? You could do it. Now, do you understand? So I really want you to understand what I said earlier. Cosine 2x kicks a lot of ass, because all you got to do is put a 2x in, and you're done. Tangent x, shit. Do you want to do this forever, or would you rather do the process where you figure out the derivatives, the tangent, and you put the numbers in? So I really want you to understand, if you understand what I said earlier about if I know Maclaurin series for a bunch of functions, I can just kind of mess with them to get other ones. This is what you might have to do for some of them, in which case you're like, I think I'll do the process. I think I'll go back and do f prime and f double prime. I think I'll do that. I think I don't want to do this. Yes? Yeah. Maybe? Okay. So, let's leave this up here. What I want to do is I want you, in fact, somebody had a suggestion for this already. That integral has been sitting up there basically this whole time. If I asked you to integrate this before we got to this section, what would be a really good method to try? Will U sub work? No. Hell no. So what's the next thing up from that? By parts, right? So what would you try to do? So U equals sine x? Now let's think about that. Let's think about it. That would mean dv would have to be 1 over x, yes? Yeah. Which means I'm introducing a natural log into my second integral. Do you understand what I'm saying? So you can think ahead a little bit. Do you want to try to do that? Because wouldn't my, so let's see where this goes. This will be natural log of x. This will be cosine x. So then I get uv minus the integral of v du. You understand? Yeah. All right, let's see. Let's try the other one. We don't care. We're Calc 2 people. We're like picking the wrong way to go as part of the process. No problem. So let's try it the other way. Let's do u equals 1 over x. And dv is sine x. What's v then? Almost.
Negative.
There we go. Yeah, there d. And then there's the d. If u is 1 over x, du is?
Negative 1 over x squared.
So then you get uv, I don't care about that part because that's e, minus the integral of v du. Minus, 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 so that's still a minus. All right, now what do you think about that integral? Is that going in the right direction? Do you guys understand what I'm saying? If I keep going this way, won't I just get x cubed? X to the 4th, x to the 5th. Will I ever get to something that I can actually do? Okay. Do you all agree with me that as far as we know, this I can't do this with the methods that we know. It's not U sub, not by parts, definitely not trig sub. That doesn't make any sense, right? Maybe. To tell you honestly, I don't care how much you know about integration, that's not doable. There's one way to do it, and that's it. And which way? This way. So what's the integral of sine x over x? It's x minus x cubed over 6 plus x to the 5th over 1, what is it, Jeff? Is that 120? Yeah. Minus x to the 7th over whatever the shit that is. 7th is like 42 times 120. I don't know what is that? 840 times 6. I don't know what that is. Big. Plus blah, blah, blah. Over x. To be really honest, there's a better way to do this. What is the sine x? What is this in closed form? What is sine x in summation form? Does anyone have that? It's all the odd stuff, right? So it'll be 2n plus 1 over 2n plus 1 factorial. You guys with me?
Yeah.
That's a lot better than trying to go infinite numbers. Now, I have to simplify this first. Can somebody please see how that's not a big deal? I take this and divide by x, and you can see it up here. If I divide by x, all my powers just go down. If I divide everyone by x, they just go down by 1. So this captures every power down the whole thing. So I'm just gonna make this go down by 1. I'm gonna lose 1x. Do you guys see that? So this becomes this. Did I leave out I did. I left out my -1 to the n here. All over 2n plus 1 factorial. Okay, let me stop for a minute. I left out a little -1 to the n to capture these negatives. Yeah, that makes sense.
So it starts at 0? It started for
Starts at 0.
-1 to the n?
Yeah, starts at 0. So -1 to the 0 is +1. Yeah. Now, real quick, does this look disgusting to anybody? Does this look disgusting? All right. Why shouldn't it? Because what's the only damn thing, the only damn part of this that's not a constant according to this guy?
Oh,
X to the 2n. Is it hard to integrate x to the 2n? I really want you to understand. Everything with just n's and shit in it, the integral doesn't care. It's a constant. Who cares? All I care about is x to the 2n. So what's the integral of x to the 2n? You can do it.
X 2n plus 1
Yeah, it goes up by 1.
over 2n plus 1.
Yeah, 2n plus 1 factorial down here already. I still got to divide by 2n plus 1. Let's see. So that is the integral of sine x over x. That's what it is. So if you wanted to go from like 0 to not 0, I can't use 0. If I want to go from pi over 2 to pi, then I can just plug shit in here. And figure it out to however many decimal place accuracy I want to. It should be a little annoying that we can't get a functional answer. You cannot get a functional answer to this. You can only get a Taylor series. There is no defined function that this Taylor series relates to. Do you understand what I'm saying? If you just create a series out of nowhere, why would it ever relate to a series? This one feels like it should because it's coming from functions. But the answer to this is an infinite polynomial. That's all there is to it. There's no function for that. To be really honest, you might see something called SI of x. This is called the integral of sine function, which is really stupid because it's just saying, it's the integral of sine of x over. I don't know. I'm sorry. So it's just putting a symbol for this, which doesn't do anything for us. I'm sorry. Okay. Maybe. So if I wanted to do this integral, right? Last thing for today. Last thing. I'm going to take all this away. And then I have to give out the practice test. Oh, man. So we got more than you wanted? I understand. Can somebody look up what e to the x is? That's one of the best. Of course he is. If you remember the summation form, it's freaking beautiful. Right? So we're going to do two things with this. First thing is, what would e to the negative x squared be then? Well, what would I do? Instead of having an x here, what would I do? What do I put in? Negative x squared. So that would be the sum n equals 0 to infinity, -1 to the n, x to the 2n over n factorial. That's what e to the negative x squared is. And then I would just integrate that. This is what's called a non-elementary function. There is no functional notation for the answer to this integral. This is this. When I integrate this, I can't rewrite it as like tangent x or something. There is no functional notation to represent the answer to the integral of this series. There isn't. Do you guys understand? Okay. We've got to turn everything we've ever done around. Series exist. Some of them we give special names to, like this series, we call it e to the x. Some of them we just never gave a name to. We just, it's too many of them, Jesus. So there's a few of them we like, and we give them little names, and the rest of them we're like, I don't know what. Maybe. What would x squared e to the x be? It's exactly what you hope it would be. What would you, when you multiply something by x squared, right? Aren't there a bunch of x's in here already? How many more x's did I just multiply by? 2. So how many more x's does it get? 2 more. Hey, I mean that's too nice. Give me a break. You see that?
Yeah.
All right. So the last thing I want to do for today, not forever. Do me a favor, real quick. Do you guys remember this? I. Do you remember I? What's I? What's it equal to?
Square root of
Square root of
negative 1.
-1. What's I squared?
1.
-1. You have to go imaginary to get something that multiplies by itself, and it's a negative answer, right? What's I cubed?
Negative I.
Just keep multiplying by I, negative I. What's I to the 4th?
1.
Yes. I to the 4th is I squared times I squared, -1 times -1, 1. Okay, so what does that have to do with anything? I don't know. Oh yeah, I'm doing stuff. What is E? In fact, let's write this out. Write out some terms. 1 plus x plus x squared over 2 factorial plus x cubed, 3 factorial plus blah, 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 right? What's e to the ix? First step is mindless, right? Oh, I'm not saying that, I'm just saying you just whatever the hell's there, just put it in, right? So 1 plus ix, let me go a few more out just because. X to the 4th over 4 factorial, x to the 5 factorial. Okay. Da, da, da. So wherever I see an x, I'm going to put an ix instead, because that's now what my input is. Plus ix squared over 2 factorial, plus ix cubed over 3 factorial, plus ix over 4 factorial. I think that's enough. So I get 1 plus ix. What's I squared? -1. So minus x squared over 2 factorial. What's I cubed? Minus ix cubed over 3 factorial. I to the 4th. 1. Who cares? Right? Look at the even terms. What is this series? Even terms. It's a series we just had up here a minute ago. That's cosine. These make cosine. Look at the odd terms, right? If you take out an I, sounds painful. Don't you get x minus x cubed over 3? This will be x to the 5th over 5 factorial. That's sine. So we just showed that e to the ix equals this. Something you could never ever get unless you manipulate power series representations of things. Yes?
And that's 1, right? And that's where you get the...
No, hold on. It depends on what I plug in. So you can plug in whatever the hell you want to for x, but now you got to realize it represents an angle, right? So what is e to the I pi then? It would be cosine of pi, yes? I'm putting a pi in, so cosine of pi plus I sine pi. What's cosine pi? -1. What's sine pi?
0.
So e to the I pi plus 1 equals 0. There's that equation that's on my shirt. Right? Now, you might be able to understand that there's a ton of shit beyond this. This is the first little, oh, holy shit. But, I mean, just the fact that this somehow represents rotations. There's no way in hell you would ever guess that e to the I. First off, what's it mean to raise something to an I power? What does that even mean? Yes, that's a good question. We just did it, and we're like, there you go. Yeah. So there's a piece of this, we don't even know what it means, but we know what it equals. What? So it feels like we sort of jumped over a bunch of math shit, and we jumped over it and got to the result. Because what does this even mean, to raise e to an I power? What does that even mean? Well, apparently it means this. Why would it mean that? I don't know. So there's a ton beyond this, next to this, before all this kind of stuff. But we already know enough to get here. You could totally do this. Okay. And that's why I was wearing my shirt, because I knew we were almost there. Okay. So, yeah, this is through 11:10. If I'm you, I would definitely get into 11:10. Let me give you guys the practice test, so then you could. I will have the answer key for this on Wednesday. I'll have the quiz graded Wednesday. I'll have any homework you give me by today. I'll give it back to you Wednesday. And you can stay for the test next Monday. Yours is coming there.
So does this mean e to the I pi is -1 or no?
Either